Hello everyone, I am from DA-IICT College and this is our course of Network Performance Analysis by Professor Ashutosh Bhatia sir, and this video is part of our course. I am Harsh Jasolia and this is my team. The main purpose of this video is to analyze TCP congestion control mechanism, but for that we need to understand some basics of TCP. So we will also see the flow control of TCP. Transmission Control Protocol, known as TCP, is a more sophisticated transport protocol, is one that offers a reliable connection-oriented byte stream service. There has been some serious issue to the potential of large-scale internet collapse due to network overload or congestion. So far, the internet has survived, but there has been a number of incidents throughout the years where serious problems have disabled large parts of the network. Some of these incidents have been a result of algorithm used or not used in the TCP. Now we will see about flow control in TCP. To see how the sending and receiving sides of TCP interact with each other to implement reliable and ordered delivery, consider the situation given in the figure. TCP on the sending side maintains a buffer. This is called a send buffer. This buffer is used to store data that has been sent but not yet acknowledged, as well as that has been written by the sending application but not transmitted. On the receiving side, TCP maintains a receive buffer. This buffer holds data that arrives out of order as well as data that is in the correct order but that the application process has not yet had the chance to read. Looking first at the sending side, 3 pointers are maintained into the send buffer, each with obvious meaning. Last byte acknowledged, last byte sent, and last byte written. Here we can see some formula. Last byte acknowledged is less or equal to last byte sent. Since the receiver cannot have acknowledged a byte that has not yet been sent, and last byte sent is less or equal to last byte written. This is very obvious since TCP cannot send a byte that the application process has not yet written. Also note that none of the bytes of the left of last byte acknowledged need to be saved in the buffer because they have already been acknowledged, and none of the byte to the right of last byte written need to be buffered because they have not yet been generated. So the similar set of pointers are maintained on the receiving side also. Last byte read, next byte expected, and last byte received. This is same as we have seen before. The inequalities are a little less intuitive, however, because of the problem of out of order delivery. The first equation is last byte read is less than next byte expected is true because be read by any application until it is received, and all preceding bytes have also been received. Next byte expected points to the byte immediate after and latest byte to meet these criteria. So next byte expected is less or equal to last byte received plus 1, since if data has arrived in order, next byte expected points to the byte after last byte received, whereas if data has arrived out of order, then next byte expected points to the start of the first gap in the data as in the figure. That is why we have include here plus 1. Note that bytes to the left of last byte read need not be buffered because they have already been read by the local application process, and bytes to the right of last byte received need not be buffered because they have not yet arrived. Same as we have seen in transmission side. Actually, now we will enter to the actual flow control discussion. As we know in sliding window protocol, the size of the window sets the amount of data that can be set without waiting for acknowledgement from the receiver. Thus, the receiver throttles the sender by advertising a window that is no larger than amount of data that it can buffer. Observe that TCP on the receiver side must keep last byte received minus last byte read must be less or equal to maximum receive buffer. To avoid overflowing its buffer, we must be follow this equation. Advertised window is equal to max receive buffer minus next byte expected minus 1 minus last byte read. This is also we can see from the figure we have seen before here, which represent the amount of free space remaining in its buffer as data arrives. The receiver acknowledges it as long as all the preceding bytes have not yet arrived. TCP on the send side must then adhere to the advertised window it gets from the receiver. This means that any given time it must ensure that last byte sent minus last byte acknowledged must be less or equal to advertised window. The sender computes an effective window that limits how much data it can send. Effective window is equal to advertised window minus last byte sent minus last byte acknowledged. Clearly, effective window must be greater than 0 before the source can send more data. It is possible, therefore, that a segment arrives acknowledging X bytes, thereby allowing the sender to increment last byte acknowledged by X. But because the receiving process was not reading any data, the advertised window is now X bytes smaller than the time before. In such a situation, the sender would be able to free buffer space but not to send any more data. Now we have some more equations. Send side must also make sure that the local application process does not overflow the send buffer. That is, last byte return minus last byte acknowledged should be less or equal to maximum send buffer. If the sending process tries to write Y bytes to the TCP, then last byte return minus last byte acknowledged plus Y must be greater than max send buffer. The TCP blocks the sending process and does not allow it to generate more data. It is now possible to understand how a slow receiving process ultimately stops a fast sending process. First, the receive buffer fills up, which means the advertised window shrinks to 0. An advertised window of 0 means that the sending side cannot transmit any data. Even though data it has previously sent has been successfully acknowledged, finally not being able to transmit any data means that the send buffer fills up, which ultimately causes TCP to block the sending process as soon as receiving. As soon as receiving process start to read data again, the receiver side TCP is able to open its window back up, which allows the send side TCP to transmit data out of its buffer. When this is eventually acknowledged, last byte acknowledged is incremented, the buffer space holding this acknowledged data become free and the sending process is unblocked and allowed to proceed. Now let's talk about possibility of these equations. As last byte received moves to the right, meaning that the advertised window potentially shrinks. Whether or not it shrinks depends on how fast the local application process is consuming data. If the local process is reading data just as fast as it arrives, then the advertised window stays open. It means that advertised window equal to max receive buffer. So it is possible. If the receiving process falls behind, perhaps because it performs a very expensive operation on each byte of data that it reads, then the advertised window grows smaller with every segment that arrives until it eventually goes to 0. Now we will come to the actual point, congestion control. TCP congestion control was introduced into the internet uh, in the late 1980s by Van Jacobson, roughly 8 years after the TCP/IP protocol stack had become operational. Immediately preceding this time, the internet was suffering from congestion collapse. Hosts would send their packets into the internet as fast as the advertised window would allow. Congestion would occur at some router and it causing packet to be dropped, and the host would time out and retransmit their packet, resulting in even more congestion. The idea of TCP congestion control is for each source to determine how much capacity is available in the network, so that it knows how many packets it can safely have in transit. Once a given source has these many packets in transit, it uses the arrival of an acknowledgement as a signal that one of its packets has left the network and that it is therefore safe to insert a new packet into the network without adding to the level of congestion. By using acknowledgements to pace the transmission of packets, TCP is said to be self-clocking. Determining the available capacity in the first place is no easy task. To make matter worse, because other connections come and go, the available bandwidth changes over time, meaning that any given source must be able to adjust the number of packets it has in transit. This section describes the algorithm used by TCP to address these and other problems. We will see that there are actually quite a few variants of TCP congestion control in use today, and researchers continue to explore the approaches to addressing this problem. So there are three mechanisms that widely used for congestion control. First is AMID, stand for additive increase multiplicative decrease. Second is slow start, and last is fast transmit and fast recovery. We will see it one by one. So first is AIMD. TCP maintains a new state variable for each connection called congestion window, which is used by the source to limit how much data it is allowed to have in transit at a given time. The congestion window is congestion control's counterpart to flow control's advertised window. TCP is modified such that the maximum number of bytes of unacknowledged data allowed is now the minimum of the congestion window and the advertised window. Thus, TCP's effective window is maximum window is equal to minimum of congestion window or advertised window. And now our new effective window size is equal to max window minus last byte sent minus last byte acknowledged. Thus, a TCP source is allowed to send no faster than the slowest component. It may be the network or the destination host. So, here the problem is how TCP comes to learn an appropriate value for congestion window. Unlike the advertised window, which is sent by the receiving side of the congestion receiving side of the connection, there is no one to send a suitable congestion window to the sending side of TCP. The answer is that the TCP source sets the congestion window based on the level of congestion it perceives to exist in the network. This involves decreasing the congestion window when the level of congestion goes up and increasing congestion window when the level of congestion goes down. Taken together, the mechanism is commonly called additive increase, multiplicative decrease. The key question then is, how does the source determine that the network is congested and that it should decrease the congestion window? The answer is based on the observation that the main reason packets are not delivered and a timeout result is that a packet was dropped due to congestion. It is rare that the packet is dropped because of an error during transmission. Therefore, TCP interprets timeout as a sign of congestion and reduces the rate at which it is transmitting. Specifically, each time a timeout occurs, the source sets a congestion window to half of its previous value. The halving of the congestion window for each timeout corresponds to the multiplicative decrease part of AIMD. Although congestion window is depend in terms of byte, it is easiest to understand multiplicative decrease if we think in terms of whole packet. For example, suppose the congestion window is currently set to 16 packet. If a loss is detected, congestion window is set to 8. Additional losses cause congestion window to be reduced to 4, then 2, and finally 1 packet. Congestion window is not allowed to fall below the size of single packet, or TCP terminology, maximum segment size. It's called MSS. A congestion control strategy that only decrease the window size is obviously too conservative. We also need to be able to increase the congestion window to take advantages of newly available capacity in the network. This is the additive increase part of AIMD, and it works as follows. Every time the source successfully sends congestion windows worth of packet, that is, each packet sent out during the last round trip time has been acknowledged. It adds the equivalent of one packet to congestion window. Note that in practice, TCP does not wait for an entire window's worth of acknowledgements to add one packet's worth to the congestion window, but instead increment congestion window by a little for each acknowledgement that arrives. Specifically, the congestion window is incremented as the given formula. Increment is equal to MMS into MMS by congestion window, and congestion window size will become congestion window plus increment. That is, rather than incrementing congestion window by an entire MSS bytes each RTT, we increment it by fraction of MMS every time an acknowledged is received. Now, this pattern of continually increasing and decreasing the congestion window continues throughout the lifetime of the connection. In fact, if you plot the current value of congestion window as a function of time, you get a tooth pattern. Here you can see that the congestion window size will increasing additively. Means the size of a congestion window is increasing by 1. Whenever packet lost is occur, the congestion window size will decrease to half, and after then it is continuously increasing additively. Whenever packet lost occurs, it will become half, and so on. The important concept to understand about AIMD is that the source is willing to reduce its congestion window at a much faster rate than it is willing to increase its congestion window. This is in contrast to an additive increase, additive decrease strategy, in which the window would be increased by one packet when acknowledgement arrives and decreased by one when timeout occurs. It has been shown that AIMD is a necessary condition for congestion control mechanism to be stable. One intuitive reason to decrease the window aggressively and increase it conservatively is then the consequences of having too large window are much worse than those of it being too small. For example, when the window is too large, packets that are dropped will be retransmitted, making congestion even worse. Thus, it is important to get out of this state quickly. Finally, since a timeout is a indication of congestion that triggers multiplicative decrease, TCP needs the most accurate timeout mechanism. Now, the next one is slow start. The additive increase mechanism just described in the right approach to use when the source is operating close to the available capacity of the network, but it takes too long to ramp up a connection when it is starting from scratch. TCP therefore provides a second mechanism ionically called slow start, which is used to increase the congestion window rapidly from a cold start. Slow start effectively increase the congestion window exponentially rather than linearly. Specifically, the source start out by setting congestion window to 1 packet. When the acknowledgement for the packet arrives, TCP adds 1 to congestion window and then sends 2 packets. Upon receiving the corresponding 2 acknowledgements, TCP increments congestion window by 2 and next sends 4 packet. The end result is that TCP effectively doubles the number of packets it has in transit every round trip time. The figure shows that the growth in the number of packets in transit during slow start compare this to the linear growth of additive increase. So here you can see see that slow start is more increasing and exponentially increase the congestion window size. There are actually 2 different situations in which slow start runs. The first is at the very beginning of the connection, at which time the source has no idea how many packets it is going to be able to have in transit at a given time. In this situation, slow start continues to double congestion window each RTT until there is a loss, at which time a timeout causes multiplicative decrease to divide congestion window by 2. The second situation in which slow start is used is a bit more subtle. It occurs when the connection goes dead while waiting for a timeout to occur. As sliding window algorithm works, when a packet is lost, the source eventually reaches a point where it has sent as much data as the advertised window allow, and so it blocks while waiting for an acknowledgement that will not arrive. Eventually a timeout happens, but by this time there are no packets in transit, meaning that the source will receive no acknowledgements to clock the transmission of new packets. The source will instead receive a single cumulative acknowledgement that reopens the entire advertised window. But as explained above, the source then uses slow start to restart the flow of data rather than dumping a whole window's worth of data on the network all at once. Here the figure shows how TCP's congestion window increase and decrease over time, and so illustrated the interplay of slow start and additive AIMD. Here you can easily see that from starting the congestion window size is increasing exponentially, and after waiting some time, the packet lost occurs. The dot is correspond to packet lost, and whenever packet lost occurs, the congestion window size falls to 0, and after then it will start increasing by exponentially till the previous congestion window size is getting half. So here you can easily see that the packet lost is occur here, then going to 0, congestion window size is going to 0, and then after increasing exponentially till the half value of the previous congestion window size, and then after it will additively increasing till the packet lost is occur. There are several things to notice about this graph. The first is the rapid increase in the congestion window at the beginning of the connection. This corresponds to the initial slow start phase. The slow start phase continues until several packets are lost at about 0.4 seconds into the connection, at which time congestion window flattens out at about 34 kb. So we can easily analyze this graph using a slow start mechanism. Now we will see some examples of a slow start and also AIMD. So first we will see the example of slow start. Here the problem is given that the total number of packets to be sent is 25 and the lost packet is 14th, 20th and 24th. So find the number of RTT round trip time required to send 25 packets using slow start mechanism. So first of all we have seen slow start mechanism. So the round trip time is 1. When round trip time is 1, the packet is sent, first packet is sent, and after then we will increase it by exponentially, means we will increasing it by double. So whenever round trip time is 2, we will send 2 and 3, and round trip type RTT is equal to 3, we will send 4 packets, 4, 5, 6, 7. RTT is equal to 4, we will send 8 packet, 8, 9, 10, 11, 12, 13, 14, 15. But here 14 people 14th packet get lost, so we will have to decrease congestion window size and congestion window size to 1 and retransmit this packet. So 5th RTT will send only one packet, number 14, and then after it will increase exponentially. Till the half value of the previous one. So 6th RTT time we will send 15 and 16. 7th we will send 17, 18, 19 or 20th. Or here 20th packet get lost, so we will have to send retransmit 20th packet. So 8th RTT we will send 20, and then after we will increase by 2, it will 21 and 22, and then 10th RTT we will increase it additively, means here the value of this window is 4 and the half of this window is 2, so we will not going to increase it exponentially whenever the value is get 2. So 10th RTT we will send only 3 packets, 23, 24 and 25. 24th packet will get lost, is lost, so we have to retransmit 24th packet. So in 11th RTT we will send 24, and 12th RTT only one packet is left, so we will send 25. So here we notice that total 12 RTT is required to send 25 packet successfully using slow start mechanism. Now we will also see the example of AIMD. The same example, 25 packet we have to send, 10th, 15th and 20th packet is getting lost. So find the number of RTT. So in AIMD we will increase it additively, means we will increase it by 1 every RTT time. So whenever first RTT we will send first packet, on second RTT we will increase it by 1, means we will send 2 packet, 2 or 3, and then we send 3 packet, 4, 5, 6, and then we send 4 packet, 7, 8, 9, 10. But here 10th packet is lost, so we have to retransmit 10th packet. But here the congestion window size will become half, because it is additive increase, multiplicative decrease. So here we will send 2 packet, as our previous congestion window size is 4, so we will send 15 and 16. In 9th RTT we will additively increasing this congestion window size, so 17, 18th, 19th, and then increase by 1, we will send 4 packet, 20th, 21, 22 and 23. The 20th get lost, so we have to retransmit it. But here the congestion window size is 4, so next congestion window is decreasing multiplicatively, means it is divided by 2, means we will send 2 packet, 20th and 21. Then after we will additively increasing it continuously, so 22, 23 or 24. then we will send here 4 packet, but we left with only one packet 25. So on 13th RTT we will send only 25th packet. So total RTT time is required is 25 packet. So we can see that little bit good algorithm is slow start algorithm than AIMD. Now, the next algorithm is fast retransmit and fast recovery. It was discovered that the coarse-grained implementation of TCP timeout led to long period of time during which the connection went dead while waiting for a timer to expire. Because of this, a new mechanism called fast retransmit was added to TCP. Fast retransmit is a heuristic that sometimes triggers to retransmission of a dropped packet sooner than the regular timeout mechanism. The fast retransmit mechanism does not replace regular timeout, it just enhances the facility. The idea of fast retransmit is straightforward. Every time a data packet arrives at the receiving side, the receiver responds with an acknowledgement, even if this sequence number has already been acknowledged. Thus, when a packet arrives out of order, when TCP cannot yet acknowledge the data the packet contains because earlier data has not yet arrived, TCP resends the same acknowledgement it sent the last time. The second transmission of the same acknowledgement is called a duplicate acknowledgement. When the sending side sees a duplicate acknowledgement, it knows that other side must have received a packet out of order, which suggests that an earlier packet might have been lost. Since it is also possible that the earlier packet has only been delayed rather than lost, the sender waits until it sees some number of duplicate acknowledgement and then retransmit the missing packet. In practice, TCP waits until it has seen 3 duplicate acknowledgement before retransmitting the packet. Here in the figure we can see that how duplicate acknowledgements lead to a fast retransmit. In this example, the destination receives packet 1 and packet 2, but packet 3 is lost in the network. Packet 3 is here lost. Thus, the destination will send a duplicate acknowledgement for a packet 2 when packet 4 arrives. Again, when packet 5 arrives, and so on. When the sender sees the third duplicate acknowledgement for packet 2, the one sent because the receiver had gotten packet 6, it retransmits packet 3. Note that when the retransmitted copy of packet 3 arrives at the destination, the receiver then sends cumulative acknowledgement. Here in our case, the cumulative acknowledgement will become 6 as our last packet was sent by sender is 6. So our cumulative acknowledgement will become 6. So here in given figure, the behavior of TCP with the fast retransmit mechanism. It is interesting to compare this graph with the graph of slow start mechanism, where fast retransmit was not implemented. The long period during which the congestion window stays flat and no packet are sent has been eliminated. In general, the techniques is able to eliminate about a half of the coarse-grained timeout on a typical TCP connection, resulting in roughly a 20% improvement in the throughput or what could otherwise have been achieved. Notice, however, that the fast retransmit strategy does not eliminate all coarse-grained timeouts. This is because for a small window size, there will not be enough packet in transit to cause enough duplicate acknowledgements to be delivered. Given enough lost packets, for example, as happens during the initial slow start phase, the sliding window algorithm eventually blocks the sender until timeout occurs. Otherwise, the graph is same as slow start. So far, our conclusion is very straightforward. Congestion control mechanism will improve the performance of TCP. Fast retransmit is better mechanism than slow start and AIMD. Fast retransmit improves 20% performance of from slow start. So it is very good algorithm right now, which is used in TCP Reno and TCP Tahoe. This is called fast retransmit algorithm. Thank you.